Anyway, it's our good pleasure. Great. So welcome everyone to UCLA Combinatorics seminar. It is my distinct pleasure to have the first out-of-town participant in a while, Leonid Petrov, who came to us from University of Virginia and the Maserati, who will tell us about Schur rational functions and the rest of the title. Welcome.
Thank you. Yeah, it's a great pleasure to be here at UCLA, where I had the privilege to be on the last pre-pandemic conference at IPAM in February 2020. It was a good time. We were kind of joking, is it serious or not? Is it gonna hit us or something? Guess what? Okay. So I was so it's joint work with my great colleagues Amal Agarwal, Alexei Borodin, and Michael Wheeler. And we had a very long preprint right now, so you don't have to read it. And thanks for coming today. And I'm going to tell bits from that. Of course, I cannot discuss everything. So this combinatorics seminar and this work is at the border of algebraic combinatorics and probability. And I'll start from the algebraic combinatorics side. And the most favorite object of algebraic combinatorics is, of course, Schur polynomials. And so I'm going to discuss vertex models related to Schur polynomials and then generalizations. So that's over there as a Schur symmetric polynomial is given the double alternate formula, the ratio of two determinants. And here's an exercise for you. So an equivalent way of producing a Schur polynomial is to, of course, do certain weighted sum over semi-standard Young tableaus of shape lambda. But if you massage this a little bit, there is a bijection with objects of this sort. So these are configurations of what I call vertex model. That's coming from stat physics. And in this vertex model, I impose certain boundary conditions it's an integrable lattice model, so I'm living on the lattice. I impose certain boundary conditions, and boundary conditions depend on lambda. So the paths in orange, they enter from below, and they are at coordinates lambda I plus n plus 1 minus I, meaning shifted parts of lambda, and then all the paths have to exit from the right. And then to each such configuration, I associate a weight, which is a product of local vertex weights. So it's kind of a Boltzmann weighting. And I'm then taking the partition function, which I denote by capital Z of a picture. And an easy exercise is to show that partition function of this vertex model with these weights downstairs is equal to the Schur polynomial. So the weights. So for the picture, I take the weight, which is a product of local vertex weights, and there are six possibilities, of which I forbid one. The crossing of the paths is forbidden, so these are non-crossing paths. And then all the squares with a path. So a vertex here in this interpretation is just a lattice square. So I look at all possible lattice squares, and then I take a product of weights. So each square where there is a path gets weight 1, and each empty square gets weight xi, where I is the vertical coordinate of this. Okay? Okay? So exercise is to show that this is in bijection with semi-standard Young tableaus of shape lambda. Okay, so once we are done with that, so what I'm going to talk about is a certain far-reaching generalization of this. And so I started with 6 possible weights over here, right? And if I allow paths to cross, then what I get is a so-called 6-vertex model, where now over here, which is obstructing the view. Actually, I can hide floating meeting control. Yeah, there we go. So there we go. So there are 6 possible weights, 6 possible vertices, and then I can take any 6 generic numbers to represent the local vertex weights. And we allow paths to intersect, and then we get a 6-vertex model, which depends on 6 possible Boltzmann weights. Moreover, we can go even further, like we did in the Schur polynomial example, that the weight of a configuration locally depends on where it is in the lattice. So these AI, BI, CI can depend on the lattice coordinates. Now, that's too fancy, actually. That's too many parameters. We have to impose like an overall condition so that the model is still exactly solvable, meaning we can say at least something about it. Something combinatorial, something probabilistic, something math physical in any sense. So at the minimum, this quantity, the delta, should be constant throughout the lattice. So however you take AI, BI, CI of depending on the lattice points, delta should stay constant. Okay, and then we are going to discuss today a very, very special case where delta is equal to 0 everywhere. Now delta is the quantity that you have Yang-Baxter equation, provided the delta is the same. It's equivalent. So these weights satisfy the Yang-Baxter equation, which I'll show in. Well, it ensures integrability in such a way. People don't know anything to say with different deltas. Okay, so we are going to actually stick to the case delta equal to 0, which is the so-called free fermion point or free fermion case. But other than that, we are going to make the weights fully general as much as possible. So, for example, this is simple degeneration of what I'm going to talk about is the factorial Schur functions. So the factorial Schur functions are defined by the double alternate formula, where instead of xi to the power lambda j plus n minus j, you put a deformed product in terms of different, x plus y1, x plus x plus yk. So you have several parameters yi's, and then instead of a power x to the k, you take an inhomogeneous power. Okay, these are factorial Schur polynomials. How to obtain them from the vertex model? Very easy. You just replace one of the weights, where here you had weight xi. Now here you have weight xi plus yj. Now depends on the lattice coordinates fully. So another exercise to prove this. Okay, that shouldn't be too bad because it's a non-intersecting path and so on. So here's the fully general case. Now instead of 2 series of parameters y, xi, yj, I have 4 series of parameters. Question? No? I have 4 series of parameters now instead. So I would take vertices of 2 types. So suppose I'm just looking at one. So too bad. These are all should be fractions. I thought it's big enough, but apparently it's not. Okay, so I take 4 parameters for the red weights: x, y, w, and w, theta, y, and s. Here they are, and all these 2-row expressions should be actually fractions. Sorry about this. And like here. And now I'm allowing basically paths to intersect. So this is no longer 0. Where? Here is a minus 2. So all the powers are -2. So well, you shouldn't really worry about what these weights are. Just showing you the fully general stuff. And so there are 4 sequences of parameters. 2 of them are in the horizontal direction, like y in the factorial case, and 2 of them are in the vertical direction, like x. Now you add one more. Question? Oh, sorry. Yeah. So now you add all these parameters, and now these rational expressions, you can check that they satisfy the free fermion condition, namely this times this, plus b times b equals c times c. It's a certain rational size that you can do. These are okay. So these are all possible ways to get free fermion 6-vertex model. with as many parameters as we can, so that ai, bi, ci depend on the lattice coordinate. But now, I mean, apparently, you might think that we have for each lattice site, we have 4 parameters, because up to normalization, we had 6. Now we have one condition in 5. Then now we have normalization, so that we say that empty is equal to 1 always. Now we have 4 per lattice site. That's actually too general. We don't have actually 4 per lattice site. Instead, when we form partition functions, we actually have to restrict the generality and not have 4 times n square, but actually 4 times 2n parameters, something like that. So we have linear number of parameters in the lattice size. Okay. The weights can depend on I and j. So let me define partition functions, right? So here are weights. So I'm taking these weights and define this partition function, which is like the factorial Schur function, but we allow intersections. And the weight at a lattice site has parameter ys, which depend on the j coordinate, the horizontal coordinate, and parameter xr, which depend on the vertical coordinate. So this is f lambda. Okay. I call these 2 functions the rational Schur functions for the sake of this talk. I mean, it's not a very common name, but yeah. And so then I take these boundary conditions I call f, and then these boundary conditions I call g. So for the g, I take densely packed configuration here, and then pass exit through the top, and where the exit is determined by lambda. Okay. So these are, yeah. So the bottom line is that we take free fermion 6 vertex model and compute as many partition functions as we can. And then it turns out that we should look at these guys as if they are symmetric functions. Okay. So connectivity with the bottom? No. Any intersections? No Schubert business. Unfortunately, we cannot do this. Okay. So here is a simple limit that takes you from f into factorial Schur polynomial. Don't worry about that. So just there is a very simple substitution and a simple limit that kills 2 of the parameters, and makes it into a factorial Schur polynomial. And we also the g lambda counterparts of the factorial Schur polynomials also can be gotten, and they appeared a lot in the paper on Hooke formulas 3 of Igor and Alejandro Morales and Greta Panova. And anyway, so next slide, I'm going to display our favorite properties of symmetric functions as much as we can. So this is a free fermion model, which means that all the partition functions should be like Schur polynomials. So we should get properties like Schur polynomials as much as possible. So let's get our favorite properties. So it's going to be on the next slide. And then the slide after that, I will specialize to the factorial Schur. Okay. So the first one is the Cauchy identity. So I take a product of g lambda and f lambda and sum over all possible lambdas, and I get the product form expression. So there are some highlights because I would like to give a proof of this. So boundary conditions. G is here, f is there. Okay. There are two families of functions depending on the boundary condition. Thank you. F is like factorial Schur polynomial. You also use G and F in your paper. How come you do this? Actually, their paper G and F are switched, but that's life. So I'm going to give a proof of this, an idea of proof, which highlights the use of Yang-Baxter equation. So here is the proof. Let me walk you through it. So I better use the board to reproduce some of the pictures so that more visible. So let's pick that one. Okay, good. Okay, need the chalk. No chalk. Thanks. Okay, so you can see, well, I had introduced two families of vertices, right? So there are vertices W which depend on little w and theta, and there were vertices W hat which depended on X and R. And then I'm introducing here the third type of vertices, which is the cross vertex, which depend on X, like R, theta, W, and X, right? So these are like, then I call capital R. And then the Yang-Baxter equation tells me that if I form a partition function, meaning as like if I form Z, you know, of this with fixed boundary conditions, so it means that I fix number of paths that go through here. There are 6 numbers, which means that I have 64 possible partition functions, right? Up to the condition that the sum of these should be the sum of these 3. So I form the partition function in this way, and the Yang-Baxter equation tells me that this partition function is equal to the other partition function where I have everything in the other direction. So I have a W hat here and W here and R here. Okay. So why is this Yang-Baxter equation true? Well, there are 2 answers. One is you just check because there are 64 identities. Take a computer, you know, write a little program and check. And the other answer is a conceptual one, is that this highlights the symmetry of a quantum group type. Now, for the free fermion case, the quantum group is actually degeneration to Q equals 0, whereas usually quantum groups are some objects that correspond to, you know, that become like the usual Lie algebras at Q equal 1, but now we take Q equals 0, so it's like a crystal type limit. And in the free fermion vertex model, we get this type of structure. And okay, so how to use this to prove the Cauchy identity? Well, if I cut here, then what I get is that my left-hand side of the Cauchy identity, sum over lambda, is just a partition function of this part, because I start with n paths that go several steps up. Then I read off lambda here. And then the paths have to go through and exit through the right. And lambda is summed over, right? So then this is the left-hand side. Now let's add a bunch of things to the lattice. And when I add these guys, I have to pay some price. So this weight is not equal to 1. This weight is actually x minus w over x minus theta inverse w, which I have to divide by. So this is what it does here. And then I use the Yang-Baxter equation to take all these crosses one by one, you know, and move it to the left, which by the Yang-Baxter equation, you know, repeated application tells me that this partition function is equal to this partition function, where now nothing enters from the left. The boundary conditions should be the same. So the boundary conditions here were empty, and now they're going to be empty. Boundary conditions here far to the right were full. Now they're going to be full. And then the boundary conditions here should be packed. Now they're going to be packed. So here I get an n by n square, which gives me the partition function of the 6-vertex model in so-called domain wall boundary, right? So domain wall means a finite square where you have paths entering everywhere from below and then exiting everywhere from the left, from the right. Sorry. In the free fermion case, this thing is not a determinant of a Isargin-Korepin type like it was covered in the 1980s, but this is a simpler thing. Now you can compute this, and this is going to be this explicit product, which is sort of like a Cauchy, you know, very much deformed Cauchy determinant, because here you see, you know, y minus y, x minus x. These are like very deformed determinants, von der Monde determinants with many parameters. Now downstairs is still the feature of a Cauchy determinant. So this is what you get. Okay, so idea of proof, yes. It's just a Schur-Cauchy question. Okay, so what is this? What is this? Is it like Macdonald? Well, Macdonald has Kupagamers, but this has only double product. So this double product is more like, I mean, still like a Schur type. Well, maybe rational Schur type. So, or maybe you can think that this is a right-hand side of the Cauchy identity with a usual times dual, where usual is here, dual is up there. So that's another valid way to think about this. Okay. So now another list of properties. So there are explicit formulas for all of the partition functions, and they are of two types. So remember we had f and g, and for f I get double alternate formula, which means an analog of that. So here it is. So I take a determinant of a type of a Schur or factorial Schur polynomial, where instead of powers I get inhomogeneous powers. So these are instead of x plus y you had before for factorial Schur polynomials. Here you have rational expressions involving many parameters, and then you divide by the Vandermonde and then multiply by the deformed Vandermonde. Now you can check. You can look at this, and you see that f is actually not a symmetric polynomial if you permute x and r together. So x and r are parameters that correspond to horizontals. So if you permute two horizontals, before you had symmetric polynomials, meaning symmetric under these permutations. Now here it's almost symmetric, except that really you just have to kind of remove this factor, and then when you remove this factor, this resulting thing actually is independent of ri's and is symmetric in the x's. So what else can I get? So there is one more property in Schur polynomials, which is very important for probabilistic applications in particular. It's the biorthogonality. So for the Schur polynomials, it's an orthogonality which basically stems from the orthogonality of the powers z to the k on the unit circle. Now here we have so in one variable, that's exactly that, and then in many variables, just throw in a bunch of determinants, which I think, yeah, they're not coming, but you throw in a bunch of determinants, you get that Schur polynomials are orthogonal with respect to the inner product coming from representation theory, for example. But anyway, in one variable, it's very simple. It's just you would just have powers orthogonal on the unit circle. Now here we have an inhomogeneous biorthogonality analog, which is that you take this type of inhomogeneous power, and then you take some kind of an inverse power up to certain coefficients, and then these are going to be biorthogonal if you integrate over a contour that circles around all the y's. So there are two types of poles here, yi and s minus 2 yi, si minus 2 yi. So there are two families of poles. You have to encircle one of them and separate from the other one, and you get exactly biorthogonality. This one? Without it, it doesn't work. No, it's something like imagine that all the y's are equal to each other and all the s's are equal to each other. Then this thing would be some kind of a change of variables for the usual orthogonality of z to the k. And so these prefactors are ensuring that this is like the d of the change of variables. But now they're inhomogeneous, so you really have to make sure that the parameters are aligned. So yeah. So by the way, I mean this actually comes together with a certain formula like summation formula. So it's a kind of an inhomogeneous geometric series. So this is more or less something like x minus x tilde. Another exercise for you. So take these crocodiles, and they actually get to. I mean, it might be some constant I forgot, but basically that's what it is. So when I have orthogonality, I can take Cauchy identity and then heat it by this orthogonality to get a formula for G. But now the formula for G would be of a Jacobi-Trudi type. So here's the formula for G, and up to a prefactor, it's equal to a determinant of H lambda I plus n minus I comma J, which is exactly Macdonald's variation of whatever. Macdonald's variation on Schur theme, which is a 30-year-old paper. 9th Macdonald variation, I think. So G is equal to a Jacobi-Trudi type, where inside the determinant you get a bunch of integrals coming from the orthogonality. So that's a good formula. It's workable. It's explicit enough to be applicable to probability. So what else? G's actually are generalizing. They are inhomogeneous generalizations of supersymmetric polynomials, if you know Schur polynomials, if you know what it is. So if the all the y's are the same and all the s are the same, then G is equal to a supersymmetric Schur polynomial. Sorry, it's down there, but it's supersymmetric Schur polynomial. So we get a kind of a Sergeev-Pragatz type formula for G in the very general case, which involves summation of over pairs of permutations. That formula is massive and uninformative, so I'm not going to show it to you. It exists in the paper, and it's a very long formula. It takes a whole page to write down. Okay, yeah. Yeah. Schur polynomials. Yeah.
Your evidence for that is that some similar formulas that work for Schur polynomials and work for F lambda.
Yes.
Except when you look at, for example, line, item box 2, there is no neither F nor G in the picture.
No, this is like in the item 2 there is B orthogonality, which for Schur polynomials reduces to the orthogonality of powers on the unit circle. Powers z to the k is orthogonal to z to the L bar on the unit circle. Okay. Now here I replace z to the k by this big product and z to the minus L by this big product. Now because F involves phi and G involves psi here. So you take, like, if you have a formula for F and you have a Cauchy identity, then you hit Cauchy identity by orthogonality by extracting the coefficient by G. Right? This is what you get. You can get Jacobi-Trudi by the same argument. Good exercise again. Of orthogonality? No, or yes. Well, this is the hardest, one of the hard. I mean, as opposed to like this is the hardest item, but this one, yeah, okay. This one is the next hardest. So to prove this, you need to compute. I'll explain what you need to do. I mean, it involves Young-Baxter a little bit. Okay, factorial Schur. So last piece on symmetric functions. So factorial Schur, everything kind of boils down to simpler formulas. Okay, so factorial Schur polynomials, orthogonal guys. This product, I mean, I separate this, but you don't really need to separate. You can just put it back. It's an oversight. Then orthogonality, and then symmetric formulas. So there are determinantal formulas with integrals, which are similar to that paper of MPP, and it computes an explicit partition function in a determinantal form, and we get a Cauchy identity for factorial Schur polynomials. So there was another Cauchy identity by Molev for factorial Schur polynomials, which these guys are different from. So anyway, this is a specialization like a breathing space, not overwhelming slide. I hope this has only one extra sequence of parameters. I hope this is more understandable. Okay, so before I get, so let me discuss a little bit how to define probability, and then after that I'm going to explain how to compute some things. So if you define, if you have a Cauchy identity, then you can define probability distribution on lambdas by normalizing. So you divide by the right-hand side of the Cauchy identity, then you get some things, some weights which sum to 1, and they're positive in case there are some inequalities. So you impose some inequalities on the parameters, and if these inequalities hold, then all the vertex weights are non-negative. So all the F and G are non-negative, and all the products are non-negative. So everything becomes probabilistic, and we get a random picture like this. So it's a probability distribution with overwhelming number of parameters, but so that vertex weights are non-negative. Yeah, so you get, yeah, you impose, yeah, the simplest possible. I mean, this is like classifying positive specializations of Schur polynomials, which is much harder if you pose the question generally in an algebraic sense. Now here it's not an algebraic sense because I don't know which algebra I'm talking about. Right? So I'm just specializing variables, and that now it's an easy question. Right. So if you take this path ensemble, you can also impose dominoes on it, and you get a domino model where it's an equivalent formulation of the same thing, where now I'm taking a semi-infinite strip, infinite to the right. I cut several one by one corners here down, then the paths you see and the dominoes you see, and the dominoes have weights which are depending on lattice coordinates, and they're expressed in this in the same format, you know, all these ratios of all the different parameters. But thanks to the free fermion structure, the domino model is a model of non-interacting dominoes. If I were, like, remember I put delta to 0 in the beginning. I said let's consider 6-vertex model, but let's boil it down to a free fermion case. Now the free fermion case ensures that the dominoes are not interacting, meaning the only interaction between dominoes is a fermion type, so that two dominoes cannot occupy the same location. If I were to take delta not 0, then it would be interacting dominoes, which mean much more complicated probabilistic model. Now here it's a dimer model, and we probabilists like this because we can compute multivariable asymptotics. So one of the similar dimer models is that of plane partition. So it's an analogy, and our model might degenerate to plane partitions, but I'm not going to explain how. So let's just consider the model of plane partition. So what's a plane partition? Plane partition in a three-dimensional interpretation is that you take an empty room, and then you take 1 by 1 by 1 cubes and stack into the corner. So you stack some number of boxes, and then I'm drawing paths on top of the boxes, like level lines. You know, I'm slicing this in this direction so that you see analogy with paths, right? And then z, which is a partition function, so then I assign a weight to each plane partition to be proportional to q to the volume, where volume is the number of boxes it contains. Q is a number between 0 and 1. Volume, here you can compute that volume is 15, example. And then the partition function, which means the sum of all weights, q to the sum over all plane partitions of q to the volume, is equal to this beautiful product. So that product should be taken by analogy with that big product I showed. And then it's a dimer model, like I showed, and the dimers are now rhombuses instead of dominoes, but still good. And so what people can do, was done 20 years ago by Okounkov-Reshetikhin, is a large size limit when q goes to 1. And when q goes to 1, you favor larger plane partitions with more boxes. And as you rescale, you get a limit shape, which you can see on that picture. And as you zoom around one point, you get a so-called bulk distribution, which is a translation invariant measure on tilings, on rhombus tilings of the whole plane, satisfying certain conditions. And this this bulk distribution is what's called the determinantal point process, which is described explicitly. By determinantal, I mean that probabilistically, you know, joint distributions of lozenges at any different number of locations is explicit and is given by determinants. In any case, so this is something analogous to what we did in that paper as a probabilistic outcome. So I don't think I'll get to any other probabilistic outcomes today, but this is morally very similar. So instead of this model, we take our model with many parameters, then we send, you know, number of variables to infinity, and we take zoom around certain location. Then we describe explicitly distributions like that. And we obtain deformation of the so-called pure Gibbs states. We obtain the deformation of something that's known from 20 years ago by means of introducing 4 sequences of parameters. So previously people didn't know that, but now we introduce 4 sequences of parameters into something well known from the integrable probability and math physics side. Anyway, so in the last 10-15 minutes, let me explain how to compute some things. So how to get proofs of the formulas and how to get the structure. So let me get explaining. So when we talk about lattice vertex models, we can describe them in terms of algebraic beta-ansatz. These are scary fancy words, but what it means is that we are talking about linear operators in tensor products. So if you take just a single vertex, then to the single vertex in the 6-vertex model, we associate 4 operators acting in C2. So I take C2 with the basis E0, E1, where E0 corresponds to no arrow, and E1 corresponds to an arrow, or correspond to a path. And then A, B, C, D operators, they act from the space of corresponding to this half edge to the space corresponding to this half edge. And the names A, B, C, D correspond to indexing of the left and right pieces. So for example, B, it acts on E1 by multiplying by weight of this vertex and returning E0, which means that you take E1 and then you map it to E0. And when you act B E0, what do you get? Yeah, W is a number. W is a number, the weight of this vertex. So if you take B E0, what do you get? 0, exactly, because of the boundary conditions that you want kind of to take out a path, but there's no path, so you get 0. So A and D are diagonal, and B and C are of the like they do not act diagonally. Okay, and then from the vertex model, there are 2 structures that is associated with these ABCD operators. One is that ABCD know how to act in tensor products, because when I stack 2 vertices together horizontally, then I can describe this by a tensor power of C2, right? So I have two configurations here, 2 configurations there. So I have 4 configurations, meaning 4 basis vectors. Now the proper structure is the tensor power. And so, for example, a B of B acting on V1 tensor V2 is a combination of 2 events, right? B corresponds to 0, 1 boundary conditions, and then there are 2 ways to lay paths on these under these boundary conditions. So B V1 tensor V2 is equal to B tensor A plus D tensor B, E tensor B. Okay. Now this actually is surprisingly general. If you take K states, K vertices, and L vertices, and then stack them together, you still get the same formula. Very good. And now I'm on a lattice, so I know how to stack them like this. This corresponds to tensor products. And now I would like to stack them like this. And for this stacking, I get Yang-Baxter equation. And the Yang-Baxter equation tells me how ABCD satisfy quadratic commutation relations. So Yang-Baxter equation is equivalent to a bunch of quadratic commutation relations on ABCD. For example, like this. This is one of the examples of the quadratic commutation. And then basically all the functions f and g are represented as matrix elements of products of operators. So f is a matrix element of a product of b operators acting in a big tensor power. So I take a tensor power because f is a partition function, right? So f is a partition function like this. So f is a partition function like this. So I need to take a tensor product to cover this layering, and then I need to take a usual product to cover this layering. And then it's going to be a matrix element of this object. So this is the essence of a piece of the algebraic beta-ansatz. And so so how to get determinantal formula for f? well, you compute this stuff. You compute this stuff using quadratic commutation relations and relations like this. Why do you get the determinantal formula? It's a kind of a free fermionic miracle, which comes from the fact that, well, this first part, the tensor action, is fully general. It doesn't depend on which weights you take. Now, these coefficients, they really depend on the free fermion nature, and they simplify commutation relations. And so because the commutation relations are simpler, you get determinants as opposed to something more bizarre. So that's a kind of a right. So so now I would like to talk about correlations and how to use operators A, B, C, D to compute more for the probability ensemble. This is probably going to be my last thing I'm going to explain. Right. So right. So let me take here. So I'm going to use A, B, C, D operators to write down the probability weights. So F is the matrix element of the product of B's, and G is a matrix element of the product of D operators. And now here I need to take some kind of an infinite volume limit so that my A, B, C, D operators, they actually would like to act in an infinite tensor product, two-sided infinite tensor product. This is needed for some commutation relations to be simpler. So I need to normalize by, so I need to take infinite volume limit. This thing, the weight of the top thing doesn't make sense. The weight of the bottom thing doesn't make sense, but the ratio makes sense and has a well-defined action. So these are kind of operators that act on in the Fock space, which is spanned by. So it's a subset of the infinite tensor product, where you only allow basis vectors that are densely packed, that the arrows are densely packed to the left and empty to the right. So now from A, B, C, D, you have infinite volume limits, which I call AZ, BZ, so on. So F and G are still matrix elements of these operators. And now I can take kind of a linear algebraic approach and realize the probability coming from the Cauchy identity as a matrix element. Well, so this probability is going to be the matrix element that you take, one of the vectors that is packed, that has n to the right of 0 and then densely packed to the left. Then you hit it with a bunch of d's, and then you project onto the single lambda, and then you hit it with a bunch of b, and then you take a matrix element corresponding to another configuration. So this, I'm sorry, this is down there. Yeah, you don't really see that maybe, but hopefully makes sense. Why, what exists? Which limit? Oh, this limit. This is because you have to be careful and define the limit in a specific way, right? So if you start with, so it doesn't exist acting on any vector, but it exists acting on semi-infinite. So you can think of a projective limit maybe. You take something non-trivial, and then you complement it by emptiness from the left, finite number of empty sides, and then finite number of full sides to the right, and then you take the limit here. But then because you divide, you divide by, so with these boundary conditions for the A operator, you would have infinitely many, like this doesn't make sense. Why doesn't it make sense? Because it has infinitely many vertices of this type. Let's divide by infinitely many vertices of this type. In the ratio, there will be only finitely many vertices differing. And here as well, it will have infinitely many vertices of this type. Let's divide by infinitely many vertices of this type. So it's canceled out. So it's a kind of a limit of matrix elements corresponding to semi-infinite subsets. Okay, so now I would like to compute correlation functions of this measure, meaning that, so by definition, the correlation function is a probability that my random arrow configuration contains a given finite set of entries. And we know that, why do we need to compute this? Well, because we know from the work of Rikanian and Castelline and temporally Fisher that this should be a determinant, because it's a model of non-interacting dimers. But we want K explicitly. So how to compute it? Well, we have an algebraic model for that. So instead of so if I take I lambda, which was a projection onto a single basis vector, then this would be a probability of lambda. But now instead of I lambda, I insert some kind of an indicator that lambda contains A1 and lambda contains A2 and lambda contains AM. This indicator is written nicely in terms of a product of annihilation and creation operators. So psi operators are operators which psi adds an arrow at A, and then psi star deletes an arrow at A, and then these guys are giving me a correlation function. And then basically I use commutation relation between certain combinations of psi and A's and B's and D's to compute this thing. So let me maybe show you the end result. So right, so basically, yeah, so we don't, yeah, we actually, if we put small psi, then we don't know how to compute them. So I would like to compute this explicitly, right? It's a correlation function, so I'd like to compute it. I cannot. So instead of computing this, I take I sum over A1 and take a generating function in A1, and a special generating function in A1, then a special generating function in A2, and right. So I have generating function. Yeah, 3 more minutes, right? So I have generating functions like this. So I have a generating function of psi operators and psi star operators with some coefficients. And turns out that these coefficients, these generating functions, they actually have the form of the same B and D, B, C, and D operator combinations of my beta-ansatz operators. And for beta-ansatz operators, I know commutation relations coming from Yang-Baxter. So everything kind of follows from Yang-Baxter ultimately, but you have to work for that. So you take these combinations of operators with special parameters, which turn out to be linear combinations of creation and annihilation operators. And then if you plug them in, so so this product was with little psi. Now I put big psi here. So these are linear combinations, infinite linear combinations of little psi. And now this I can compute by commuting. So we commute out, commute everything that kills this guy. We commute close to this guy so that they kill it as much as possible. And then everything that kills the other one, we commute to the other side and so on. So we use lots of commutation relations to get an explicit determinantal expression. And the last piece is to extract the coefficient. Right? We take generating function, then we extract the coefficient. And so we get a determinant where the correlation kernel is somewhat explicit. It's given by double contour integral formula of some elementary products. Right? You see elementary products, and it generalizes a bunch of known determinantal kernels for domino tilings and lozenge tilings and Schur processes, like that. So even though the work is 119 pages, but it was informed by more work before. So it was informed by Schur polynomials and Schur processes by Okounkov-Reshetikhin, and some domino tiling work by Kurt Johansen and others. And yeah, so there is a lot of things that we know, and we know how to apply it to this model. Okay, so this is the kind of an end result for probability. Like, okay, so it's an explicit computation with which we can do asymptotics, which basically I showed you for the plane partitions. So we take some limit, get some limit shape, we get the analog of translation invariant distribution, the whole plane, an explicit determinantal kernel. So let me skip through this. Right. So here's a summary. So we take a probabilistic model with many parameters that's based on multi-parameter generalizations of Schur polynomials. And the seed here is the free fermion 6-vertex model. So what we get is we get just generalizations of factorial Schur polynomials and usual Schur polynomials to more parameters, and we get a probabilistic component, which is Schur process-like, plane partition, random plane partition-like, and we get the limit in the bulk of the system, the lattice limit, which depends on many parameters. And one of the the technical features, there are basically two technical things that we figured out. One is that you can take A, B, C, D algebraic beta-ansatz operators that they spent. I hope, I mean, it was in the middle of the talk, but it was probably understandable, at least a little bit. So you take A, B, C, D operators based on vertex weights, and they know how to act in tensor products, and they also satisfy quadratic commutation relations. So this is the essence of the algebraic beta-ansatz. And you can use this to build up fermionic operators, which are creation and annihilation type operators, which then can be used to compute correlation functions. So this is one technical feature, and the other one is the kind of an inhomogeneous fermionic operators, inhomogeneous boson fermion correspondence, and inhomogeneous calculus for extracting coefficients from generating series, where instead of generating series with z to the k, you take generating series with psi k, right, with the inhomogeneous powers, inhomogeneous power analogs, right? So you can take a generating function, a Taylor or Laurent series, and then there is an analog of a Cauchy integral formula to extract this coefficient, which I basically showed you because this is the same as this orthogonality. This one. So this is a kind of a inhomogeneous Cauchy integral formulation. Okay, so I stop here. Thank you very much.
I know this was a little shock and awe. Lots of formulas, and we started with Schur functions, and suddenly there are all these parameters, and there's so much, it's even hard to figure out how to ask a question. So maybe you should also tell us what question should we ask and answer.
Yes. Well, there was a question. Pasha, there was first, yeah. Those paired up to make here. So if you pair them up like this, then what you get is linear combination of creations. So you pair up infinite volume limits of it's a certain computation that you need to do. So it involves first computing before the limit, then after the limit, it becomes this. So what is Yang-Baxter moves? Mm-hmm. Yeah. Yeah, that's not. Yeah, that's not right. So. Okay, so ABCD operators, they satisfy Yang-Baxter, and it's equivalent for them as in the form of quadratic commutation relations. So what do you mean? Okay. Sorry. Yeah. So it's asked. What is asked exactly? Okay. What these guys? Which boundary conditions they satisfy? So these are operators which act in the Fock space, with the basis of semi-infinite configurations, and well, the C is this operator, right? So it has full empty, and then D is the empty empty. So it's a certain computation where you take this two-row combination with special parameters and then put it on top of a vector, and then what it ends up with is that it adds so it's D and C, right? The boundary conditions that you have one extra going in and then it has to come out somewhere. So this says that it comes out anywhere it can with this weight. So this the same for D and B where you take one out. So this explains maybe something, but yes.
I think want to point in do you see like matrices with negative minors in your story somehow?
We see matrices with non-negative minors. Of course, this is a matrix with non-negative minors. So we see this matrix has non-negative minors. All minors of this matrix, diagonal minors, all diagonal minors are between 0 and 1. Yeah, principal. So all principal minors here and all principal minors here. So this one is a new object which has 4 sequences of parameters. It's an arc integral, so it also has one complex number from the upper half plane. So this is an arc integral from z bar to z, and it has the product of 2 inhomogeneous powers. So it's like a big rational product, and then you take an arc integral of it. So it's a pretty transcendental thing. Now you take this matrix, it has all principal minors between 0 and 1. All non-negative and less than 1 because it's a probability. It's right. So I didn't show you because maybe you don't appreciate this. You're not probabilists here in the audience, but in a very particular case, this comes up to the matrix which is the discrete sine kernel. Now this thing also has diagonal minors which are all non-negative and between 0 and 1. So this is a special case of that. All minors non-negative. No, these guys don't do that. They allow negative minors. I'm pretty sure of that. Check, but I'm pretty. Thank you.